Hello everyone. So firstly I would like to thank the members of the committee for organizing this conference. This work is titled Improved Intensity Based Image Registration via Archimedes Optimization Algorithm, and this work was carried out in the Engineering Systems and Application Laboratory under the direction of Mr. Sayyouri. So, this work proposes a new algorithm for intensity-based registration via the Archimedes optimization algorithm using the 2D affine transformation as the geometric transformation and the normalization of the sum of square differences as the similarity metric. So the outline of this presentation starts with an introduction to image registration, followed by a presentation of intensity-based image registration, and as a third axis we will present the geometric transformation and the similarity metric used in this work. Fourthly, we present our new method for intensity-based image registration based on the Archimedes optimization algorithm. Then we will discuss the simulation results, and finally we will conclude our presentation and give some perspectives. So in the last decades, image registration has attracted growing attention from researchers. In general, image registration is a method of geometrically aligning two or more images by matching them to each other. And there are several image registration techniques, and the most popular of which are feature-based registration and intensity-based registration. As there is also the hybrid image registration technique, which combines the two techniques mentioned. So in the following, we will propose a new algorithm for intensity-based registration to find the parameters of the geometric transformations needed to align the images based on the Archimedes optimization algorithm. Now I am going to explain the loop of the intensity-based image registration. As we have already seen, intensity-based image registration is an image processing technique that aims to align two or more images according to their intensities. So the flow chart for this technique is shown in this figure. So firstly, two images are taken, one of which is desired image and the other is the current images. Then a geometric transformation is applied to the current images. Next, the similarity between the transformed images and the desired images is calculated. So if the stopping criterion is met, the result is good, but if not, another estimate of the transformation parameters is made using an optimizer. And this loop is repeated until a better match between the two images is obtained. In this section, we will talk about the tools used in this work. So in this field of images processing, several geometric transformation can be used. In our algorithm, we use the 2D affine transformation, which is defined by 5 parameters. So 2 for translation, and 2 for scaling, and 1 for rotation. And regarding the similarity metric used uh, in this field, there are several metrics can be used. Uh, so in our work, we have selected the normalization of the sum of squared differences, which is defined by this relationship. So in this work, we have adopted the Archimedes optimization algorithm, which is effective in several applications and superior to many other optimizers. And the 9 steps in this method uh, are described below. So step 1, the target and actual images are analyzed to superimpose them after this method. Step 2, initialize parameters, the position, volume, density, and acceleration of all objects or uh, population. And step 3, update the densities and volume of an object E. So step 4, calculation of the density factor and transform operator. So step 5 and 6 represent the exploration and exploitation phases respectively, in which the object's acceleration is updated. And step 7, calculating the acceleration uh, normalization. And step 8, update the position again. And finally, in step 9, we have the selection of the object's position with the best fitness value during the evaluation of each object. So in this section, the simulation results, we present simulation results to validate the theoretical results developed before. We also compare the effectiveness and superiority of the Archimedes optimization algorithm to the sine cosine algorithm and equilibrium optimizer via the similarity metric value obtained and the computation time for each method. And this figure shows the image used in this section. So I is current color images, B desired color images, and this images C. So the display montage of the two images. We will start our comparison with the similarity metric. As you can see from this table, the best results of the similarity metric are obtained when the Archimedes optimization algorithm is implemented for intensity-based image registration. So, as a second comparison criterion, we will discuss the speed of convergence. Based on this figure, the speed of convergence of the Archimedes optimization algorithm is faster than the speed of convergence of the other algorithms. In addition, intensity-based image registration using the Archimedes optimization algorithm required only 14 iterations to find the optimal value for the normalization of the sum of squared differences. And the last comparison criterion is the computation time. Regarding the computation time, which is a criterion we use to compare the convergence of the intensity-based image registration for these three methods, we found that the this uh, value ETIR1 is almost equal to 30 7, and this report 2 is almost equal to 9 compared to the equilibrium optimism. We therefore deduce that intensity-based image registration using Archimedes optimization algorithm is better than using sine-cosine algorithm, which is better than the equilibrium optimism. So, to finish our presentation, firstly, this work proposes a new approach to improve intensity-based image registration using the Archimedes optimization algorithm. Secondly, the simulation results demonstrated the effectiveness of the proposed method in terms of similarity metric and computation time, and consequently the improvement in the quality of the correspondence between the two images after registration compared with other methods. As future work, we will be working another research related to image registration of 3D three-dimension images, and implement and evaluate this method in the field of images-based visual survey. So, thank you for your attention.